All right, happy Monday. Let's get started. So just a quick announcement. So next week, all right, if you've looked ahead, it's a Memorial Day weekend. And so there's no school on Monday. And so, right, that means obviously no lecture. There's no lab next week because of that. But yeah, but what's going on is, so if you were in my Monday lab today, a lot of people did not make it through both labs. So we have 2 labs to get through this week, and then next week is just an off week. So if we have to do more lab makeups on Wednesday, in case people don't finish, then that time is available. So I'll just put, so no official lab. So we'll do makeups on Wednesday. So I'll be around on the Wednesday time if you still need to finish stuff up. And of course, I think some people were also planning on coming in on Wednesday to try to finish up, so that's also fine. So just try to get your labs in and make up any other labs. So people were making up labs today, so that's good, right? Get those labs made up ASAP if you're missing data. And so just kind of looking ahead to next week, we'll probably lecture then just on Wednesday. We'll use the whole time to lecture, and then probably a take-home quiz next week. So we'll still have our regular quiz right on Wednesday, but next week will be a take-home.
Is next Wednesday the 29th?
Yeah, I think that would be the 29th. All right, any other announcements, concerns, questions? We're kind of getting to the end here. We could even look at our calendar to just kind of remind ourselves what's going on. So we're basically kind of at the end here. And so next week, week 9, again, our Monday lab holiday. And then week 10 is our last lab, so that's kind of a fun one. It's just a long one. So acid bases buffer, so I would expect that to take the last, all of the last period. And then, right, no lab practicum this year, so you guys managed to get a little lucky with that since we had too many holidays and then Earth Day, so.
What is that lab practicum?
I mean, it's just an exam.
Oh, it's like the final for the lab.
Yeah, it would be the lab final, but we just don't have time for it.
I see.
Yeah, so I was just saying, we got out of it this quarter, and then just, yeah, oh darn. And, and then, of course, just looking ahead, right, we'll be doing our, so next week we'll do our solutions chapter on Wednesday. Last week, week 10, finish up any last thoughts and do acids, bases. Week 11, we'll do our Monday review and then get us ready for Wednesday exam. And then just try to finish up all the homeworks and everything. So ideally before week 11, but otherwise, you know, you have until like Sunday, 11:59 or whatever, because grades are due on that Monday generally. All right, questions, comments, concerns?
Was it the 17th? I thought the last day was the 13th.
Have to look at the other calendar. Because I think graduation's on the 15th, but then grades are probably due like that Monday, which is why it says the 17th.
Yeah, I was like, we don't have a class that week, right? 'Cause
No. Yeah, because week
I had a
11.
job lined up to start that day. I was like, wait a minute.
Yeah, that's just more for finishing up. And then if you notice, right, your stream is probably not working on Blackboard, the activity stream.
Yeah.
I was really scared at first. I was like, is everything gone?
No, it's a Blackboard system-wide error. Everyone's having the same issues, so.
I found I was able to get to everything, but just go to courses.
Yeah, so you have to go to the courses. So just be aware of that. It's not you. You haven't been dropped, you know. It's just Blackboard.
It's always Blackboard.
All right.
With how many problems they have with it, they'd figure something else out by now.
Yeah, that's technology. All right, so now we're getting into kind of our gases chapter. And this also gets into intermolecular forces a little bit more in detail. And so kind of this helps us understand like why things are solid, you know, why is water a liquid, why is sodium chloride a crystal. And so this is kind of just a quick recap, right? So what does it mean when something is a solid, a liquid, or a gas? And so of course we just remind ourselves of the basic definitions. So right, a solid, we said, has a fixed shape and volume. And then a liquid still has a fixed volume, but then just takes the shape of our container, so more movement, more fluidity. And then a gas, of course, right, no fixed volume, no fixed shape, and expands to fill our container. And then I'll add that keyword of compressible. So gases are compressible. And so now, again, we're going to dive into our gases chapter, at least initially, before we go into intermolecular forces. And so just what is a gas? So of course, a gas is just defined as our phase of matter, where our particles are moving randomly and very fast. Of course, just moving around. And we can also kind of think of a balloon. So right, we have our balloon filled with gas. And then we have some kind of just, well, how do gases behave? And so we have our assumption. And of course, right, gases just travel in straight lines until they hit, right, the wall of our balloon, let's say, or collide with another particle. And so these collisions, of course, start to combine and make pressure. And so now this is starting to get into our chapter. And again, right, we can think about our balloon and how our balloon stays inflated. And so let's just define force and pressure. So our pressure is the force exerted by a unit area by a gas as our molecules strike. And so let's think about our balloon. So our balloon, of course, is exerting pressure and keeping our balloon inflated. But of course, we have to think about, well, what is our balloon working against, right? So our balloon is hitting the inside of our balloon walls, keeping it inflated. And our balloon, of course, is working against our atmosphere. And so meanwhile, as our inside molecules are beating the inside of our balloon, keeping it inflated, right, it's working to keep it inflated against our atmospheric pressure, right? So we have 1 atm of just normal gases always around, right, beating down. And so they're trying to almost, right, deflate our balloon. So it's smacking our balloon, right, pressure. And so, of course, we have to have equal pressure on the inside, keeping it inflated. And so again, right, our gas pressure is just the result of our constant movement, so just those collisions continually occurring. And then so our pressure is dependent upon a few factors, so we'll get into, of course, quantifying this. But it depends on the number of gas particles. Of course, right, you put more gas particles in, more collisions. Our volume, and so, right, we can think about volume in relation to surface area as well, right? So you have your volume, and then again, our collisions, right, beating down on that surface area. And then usually if we expand our volume, right, increase surface area as well. So that helps to decrease the pressure versus, right, if we decrease our volume, then a lot smaller surface area, a lot more pressure. So I'll just put volume and surface area. Maybe I'll spell that out. Surface area relationship. And then, of course, average speed. So, right, if we're at just kind of 21 degrees Celsius ambient temperature, they have a certain speed. And then, of course, we can increase the temperature, right? And that increases the kinetic energy. So more higher temperature, greater speed, right? More collisions there. Questions about this so far? And so then we have this kinetic theory of gases, which is, again, kind of our more idealized view. And so we make some assumptions, and that being said, right, it may not be perfectly true for our real gases, and we'll kind of explain the deviation. And so just when we do this theoretically, we assume that all our collisions are perfectly elastic, so meaning no exchange of energy occurs. And so if this were to happen, particles and our surfaces would be referred to as an inelastic collision, where they like crumple, versus like a perfect, pool table where the billiard balls just collide. And so, right, this is kind of, not entirely true. So, right, these collisions are probably not perfectly elastic. This is also kind of ignoring the intermolecular forces, and so we'll go back and talk about that and how that comes into play. And so again, kind of the assumption with this statement is that all gases behave equally. So they're all the same, right? It doesn't matter whether they're polar, nonpolar. Again, that's not really true, but just for our kinetic theory and kind of how we treat our gases in our idealized situation. And so how do we characterize gases? And so a good character is, of course, its pressure. And we have a few units of pressure. And so millimeters of mercury and torr are used pretty interchangeably. And so what I mean by that is 760 millimeters of mercury is equal to 760 torr, which is all equal to 1 atm. And then we can see how our pressure is measured. And so this is using a mercury manometer. So we have our mercury, and of course, right, mercury is really dense, really heavy. And so then what you're measuring, so you have this, notice a vacuum tube, so right, there's no air in there. And so now your atmospheric pressure, so all your air, is beating down on this mercury. And because this is vacuumed, so that pressure of, again, our air beating down causes our mercury to rise to a certain level. And so this is where the 760 comes into play. So at, again, normal ATM, our height of our mercury column is 760 millimeters, or 29.92 inches. You might see the inches unit as well. So that's the height. And so, again, millimeters of mercury, that's why it's used. That's where it comes from. And then torr is just set the same. And then we may have other units. So just kind of be aware. So again, mainly we use torr or ATM, but just be aware of pascals. So you have 101,325 pascals is an ATM. Sometimes you see, of course, kilopascals, so that would be kPa, and so that would just be 101.325 kilopascals. And then we also have PSI, which usually you see with like your car pressure. It's usually measured in PSI. So like a typical car, at least like, a normal sedan is usually around 33 PSI for the tire pressure, somewhere around there. So So you can see right, at least 2 times our ATM, roughly. And then bar, so bar is sometimes used in like the weather. So I think those are like US units. And so notice a bar is 1.013 bars is an ATM. So kind of strange, this is a strange unit. But it, like I said, if you look up the atmospheric pressure, the local weather report, it's usually in bars. All right, so then we have our 4 basic properties of gases, and again, we'll look at some relationships between them mathematically. And so again, we have our pressure, and the common units, the SI units, are going to be ATM, and I'll point out later when it's like relevant to be in the units or not. And then volume is usually measured in liters. Temperature, though, always has to be in Kelvin. So star this, big star. So temperature always needs to be in Kelvin. So there are certain situations where like your pressure and your volume units don't matter so much, but always in Kelvin. And then we have our molar amount, so moles with an N. And so these properties, of course, are interrelated. So if we change one, we change them all. And so first we'll start off with our simple gas laws and just look at pairs of relationships, but then we'll kind of summarize it with our ideal gas law. And so here are kind of the 3 laws. So let's look at Boyle's law first. And so that's our pressure and volume relationship. And so these were pretty early experiments, so they were just messing with what's called a J tube, so it's just a little sealed tube, and then trying to measure the volume at different pressures. And so they had this trapped air sample and then added mercury to increase the pressure. And of course, this is now a piston diagram, but we can kind of see that same relationship. So let's look at our starting point. So we have our volume here at 1 liter, pressure of 1 ATM, and then write our piston with our 1 kilogram weight on it. And so now if we increase our pressure, so now they have 2 kilogram weight on it. And so they noticed 2 things, right? So notice our volume. So we shrunk our volume in half. So we went from 1 liter to 0.5 liters. And then meanwhile, while our volume went decreased by half, our pressure doubled by that same amount. So we went from 1 ATM to 2 ATM. And so this is kind of the key, right? So they noticed an inverse relationship between our volume and pressure, right? So now we're saying if volume increases, then our pressure decreases. So inverse relationship. Have you all ever played with these like PhET simulations before? So some people have, some people haven't. Let me post a link so you can kind of play with it later. So they can be kind of fun. So let's see, hold constant. Let's do nothing. Sorry, let me add some gas to this. So let's try to do our Boyle's law. And so these are just fun to kind of play with if you've never played with them. And so unfortunately, they don't have like a volume measurement here, but we can just see, okay, we're at 12.7 ATM. If we roughly just kind of half our volume, right, then we pretty much doubled it. So obviously with no measurements, this is a little hard to tell, but we can tell, you know, roughly we doubled our pressure then. So that's kind of fun to play with. All right, so let's keep looking at our laws here. And so continuing with our Boyle's law, and so we kind of get this graph here. And so again, we state that our volume of our gas is inversely proportional to pressure. But then what do you notice here? So we kind of have our graph stalling out. So what's going on there? What kind of becomes an issue at these extremes?
Could it be, such a high pressure on gas could cause explosion?
I mean, that's always a risk, but what else happens? Just think of what's our limitation eventually at the most extremes? Sorry? So can we ever get to truly zero for volume though? So what kind of happens, right, at these limits here? So this is where, right, our size kind of our atom comes into play, right? So at these most extremes, so kind of what you were saying, right, we can never truly get to zero because now we have, right, our physical atoms do have to occupy some sort of space, so we kind of get our limitations here. So it bottoms out, right? So we can only compress so much once we get to these, again, right, really extreme conditions, so super high pressure, super small volume, and then eventually, right, physical size of the atom comes into play. And so again, we have this as our pressure increases, volume decreases. And so this is again now our key formula. So our P1 V1 is equal to P2 V2. And so this is where units don't matter. So units don't matter, just need to match. And so what I mean by that, right, pressure could be ATM, as long as they're both in ATM, right, ATM, PSI to PSI. It doesn't matter just as long as they're the same. Same thing with volume, right? They could be anything, so milliliter, milliliter, you know, liter, liter, gallon, gallon, as long as they're the same. And so other kind of relevance to this is with diving. Has anyone ever gone diving in this class by any chance? Our oceanography class, so someone mentioned oceanography today, so I was thinking about it. So I taught oceanography last summer. I don't normally teach oceanography. And we went into a little bit about this because of the pressure underwater, and then that started to bring up a lot of interesting stories, so we'll get into that. And so let's first talk about the physical issues with going, of course, deep underwater. And so for every 10 meters of depth approximately, a diver experiences 1 additional atmosphere of pressure due to the weight of the water. So that's kind of intense. So at 20 meters, you're already at 3 ATM of pressure. And so then they make this statement. So if a diver, right, holds his or her breath and goes to the surface quickly, right, the outside pressure drops to 1 atm. And so what happens to your lung volume? And so because your pressure is decreasing by a factor of 3, that means your volume will expand by a factor of 3. And so this one, right, mentions damage to the internal organs. But we could talk about like other issues that come with diving, and so why they say to rise slowly. And so, right, you don't just have air trapped in your lungs, right? You have air, in your blood vessels, or like a little bit of dissolved gas all in your blood. And so that's also something to think about. And so why they say that you need to rise slowly so that, again, right, everything gets reacclimated and that you don't have, blood vessels bursting or anything like that. So that's kind of interesting. And so that's where the stories in oceanography came into play, because I think people have been in the military and like seen other people kind of do diving, and like I think there's a guy panicked and rose pretty quickly and then ended up, kind of messing up some blood vessels, had to go to the hospital. There's also, not to get down into the rabbit hole, but have you guys ever heard of like those people that do like deep sea diving as like a sport and like try to break the record and like crazy stuff? Yeah, like it's pretty fascinating. So we won't get too into the rabbit hole, but like it's just kind of crazy because that's like what they're training for. Some of them can get like really sick and like die and like even have, brain aneurysms or something because of the danger with training. And yeah, I don't know how people kind of train physically. And then of course, not to mention, the deep sea ocean creatures, so their bodies kind of have to be built to withstand this pressure. So there's lots of different things in their bone structure, which is kind of fascinating, and just how the animals process the oxygen. And a lot of those animals can be like oxygen deprived. It's kind of crazy. All right, so let's try to do the chemistry. So I'll rewrite our equations. We had P1V1 is equal to P2V2. And so now we're saying, okay, as we breathe, and so now we can do a quick bio lesson. And so, right, we inhale by increasing our lung volume. So that's your diaphragm, right? So your diaphragm goes lower, kind of physically increasing your lung volume space. And so now we're saying that we have an initial lung volume of 2.75 liters. And let's just say we're at atmospheric pressure. And then what happens if we could just increase our lung volume, right, without inhaling any additional air? So right before that inhalation, what is the pressure? So see if you can figure that one out. All right, what did we get? And so with these problems, you know, it's always a good idea to kind of write out what you're setting up as your P1, V1. And it really doesn't matter, you know, who's who as long as they're the same. So our P1, we have 1.02 ATM. And so that means our V1, our corresponding condition is 2.75, right? They could have both been P2 and V2 though. And so if this is P1 and V1, then our V2 is 3.25. So then we can just set up our problem. And, you know, in this case, we were in ATM and liters, and that's fine. We don't need to do anything. We're consistent in our units. All right, so what do we get for our pressure here? What do we get? 0.86, and I'll round it to 3. So that sounds good. Is that what everybody got? We can plug it into our calculator too. So I'll just go through it. So 1.05, oh, 1.02 times 2.75, and then divided by 3.25. So yeah, 8.63. Questions about this one or anything? So now let's look at Charles's law. Oh, sorry.
So the 2 doesn't mean I can multiply it by 2, right? Just like P1, V1, and then P1, or P2.
Yeah, so like the P2, V2, that's just the second set of conditions. No, it's just our first set of conditions and then second set of conditions. All right, so let's look at Charles's law. So now this is looking at volume and temperature. And so now it says that they have a direct relationship. So direct just means that if we increase our temperature, and again, this is assuming that everything else is constant. So everything constant. So this is but mainly referring to our pressure. So if we have to keep it at a constant pressure, but then our temperature is increasing, well then our volume, right, will have to increase to balance that out. So let's kind of play with this on our PhET simulation. And so right now we want to hold, so let's hold our pressure constant, but then I think that means changing temperature. No, I'm not sure which. Okay, I chose the other one. So I think now it's going to affect my volume. And so let's do that, right? So now we're kind of at 21 ATM. And so let's see what happens if we heat it. So it's heating it. But then we said, well, we want to hold pressure constant. So right now our volume is increasing as we keep increasing our temperature. And then, right, we can cool it back down, do the same thing. So again, we're holding it at 21 ATM. And it's now cooling it. So to keep it at that constant pressure, right, our box is shrinking.
It's like when you leave a soda can in your trunk car and it explodes all over your trunk.
Yeah, so lots of different, there's ways to kind of start to relate things. So yeah, if you have a closed system, your soda can, right, that could explode if it gets too hot, so it can't expand. And then, so this is where units do kind of matter, at least for our temperature. So temperature has to be measured in Kelvin. So the reason for that is we do not want negative temperatures. So if we have negative temperatures, that doesn't make sense thermodynamically. So we have to be on the Kelvin scale, right? So Kelvin goes from 0, all the way to positive numbers. And so you just want to be in the positive numbers. That's all that this is saying. So we have to be in kelvins, have to be in Kelvin. And then your volume, it doesn't really matter, again, what it's in, as long as you're consistent. And then now that they have a direct relationship, now their formula looks a little funny. So we have V1, T1 is equal to V2 over T2. And so again, that's for our direct relationship. And then again, we say that our volume of our gas is proportional to our absolute temperature. And again, the absolute temperature is just saying right in Kelvin, so we're always on a positive scale, and thermodynamic relevance. And so like what we were seeing with our simulation, and this right makes sense, so we increase the temperature, that starts to increase the speed, and then average kinetic energy of our particles. And so, of course, with that increased energy, if we want to keep our pressure constant, that's where we have to shift our volume. And so, of course, right, our greater volume spreads our collisions out over our greatest surface area. And so then here's our Charles's law graphically. And then, of course, it's just extrapolated at the end. And so, of course, we again have our physical limitations. So all of our gases begin to condense before we get down, of course, to 0 Kelvin, right? So this is just 0 Kelvin. Oh, that looks like okay. 0 Kelvin. So that's all that's saying, right? We have our theoretical lines here, but obviously gases do not behave like our perfect ideal gases. So that's where that comes into play. And so let's watch kind of a fun video that helps us look at this.
Hi everybody, I'm meteorologist Jay Burschback along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. And I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel. I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day. Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up. Okay. So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
All right, so it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with. See, there's a good sort of jet of steam shooting out. We're going to try to capture that
Okay.
by putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to spin it down. Well, the first thing we should hear are a couple of the ends of the drums popping in.
There we go.
A couple of the ends going in. There's the other end. There we go.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside
There it
has
goes.
cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is
to the drum.
amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can. Or if you've ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure. Yeah, no one, having that blowtorch.
The blowtorch is
Yeah, so let's talk about that. That's always a fun video. But we can kind of see, right, it was an extreme experiment of inversion of what's happening here. And so you kind of mentioned too, right, you can see this with the milk jug. And so, right, if we have something, if we put a balloon in a bunch of boiling water, so let's kind of look at the differences for a second. So this one just has a balloon kind of put in two different situations. So we can think about this probably was just a regular normal balloon. And right, if we stick that regular normal balloon in some boiling water, that will increase its kinetic energy. So right, more kinetic energy, more collisions. So it should be kind of more inflated, right? Until, of course, maybe we make it pop accidentally if we, of course, bust through the material strength. And then we can take that same balloon and put it in some ice, right? And then it gets smaller, so lower kinetic energy. And then that ice just cools it down, and so our balloon shrinks. And then, of course, right, with the imagination station, what we watched. So there are a few key points, so kind of going back in the video. And so what was the whole point of the water? So what was he trying to do with the water? And kind of what properties is he taking advantage of with water? So yeah, kind of taking up space, right? And so that's why he wanted to heat it. And so the other thing, of course, is that water, we can see all the different phases much more easily. So yeah, he had to take the water, right, and then they superheated it and expanded it so that it's occupying, right, our whole 55-gallon drum with our H2O in there. And so, right, kind of the key point, too, was once they had all that water in there, and it was hot and steam, so, all right, in its gaseous form, so we should put probably more gas there. Then the key was that they made a closed system, right? So then he closed it, so now we have a certain amount of water trapped. And then, of course, right, then they cooled it. And then, right, water, so it was probably very effective with water since, right, again, water goes back from the gas state, now back to a liquid. So now we have H2O liquid. And so probably not a lot of other air molecules in there, right? So plus whatever air. So plus whatever air. And so since a lot of that water probably displaced the air, now we're just left with our liquid. And then, of course, that's how it got so easily crushed, right, by our ambient atmospheric pressure. So kind of cool. All right, let's do our last problem here, and then we'll take our little 10-minute break. So now we have a sample of gas, has a volume of 2.8 liters at some temperature. And then we submerge the sample in ice water, and so our temperature is at 0 degrees Celsius. Its volume decreases to 2.57 liters. So what was the initial temperature? And I can at least rewrite the formula. Do we have an answer? A little more time. Well, that is the problem, right? Is you can't be in Celsius. Yeah. So don't forget what we said, right? We have to be in Kelvin. So I'll give everyone another minute. So then I'll start writing our setup. So right, we can set this to V1. So we have 2.8 liters. So again, the volume unit doesn't matter as long as they're consistent. But like you guys were noticing, so we have to be in Kelvin or else you have a weird divide by 0 already. So it's not a good start. Oh, sorry. And then I set that up wrong. So we're solving for X, which we don't know our initial temperature. But then we do know that we put it in ice water, so 273 Kelvin, and it was 2.57 liters. So then we just have to cross multiply, so 2.8 times our 273 divided by 2.57. So what do we get for our initial temperature? So do we have 297 Kelvin? Let's see, one nod. So you should get 297. You could use 273.15, but that shouldn't make too much of a difference.
Should you take away the decimals? Like, change into, Kelvin?
It doesn't matter too much, because like I said, you could use 273.15, but yeah, it probably won't change this number. So did you still get like 297? Yeah, so then roughly, right, you get like 297 Kelvin, then it asks for it in degrees Celsius. And so me personally, I just kind of ignore the 0.15 on the end, but if you include it, right, it's fine. So either way, I'm not going to be too picky on that. And then about 24 degrees Celsius. All right, let's take our 10-minute break so we can be back at around 2:02 or so. And we'll keep doing these formulas. think we're about ready to continue with lecture. I did want to remind you all about World Day that's happening tomorrow. So it's only on the Riverside campus. And it should be fun. They're supposed to have like a tea demonstration and like other fun stuff. Hopefully they have free food. I know last year they had like the Cava Empanada truck. I don't know if they're going to do that again, but just letting you know. And I'll also be out there with my Chem 200 level students, so they'll be doing some ice cream. Hopefully that will turn out okay.
Would that count for a final?
No, we can't do that, but
Extra credit?
I just thought it'd be fun to let you know so you can hopefully eat some free food and see some stuff. We're still missing Sky. She can get lost in the bathroom.
We're stuck in it. Stalls are not spacious in any way.
Oh, there she is. All right, so now let's continue. And so this one, I think, is a little self-explanatory, right? So now we have our Avogadro's law, so volume and moles have a direct relationship. And this kind of makes sense. So again, we're holding now pressure and temperature constant. And so of course, if we physically add more moles of something, and again, we're keeping our pressure constant, then we're going to have to increase our volume. So let's see. So if we want to hold constant pressure, and so let's see if this works. So now I add more moles to it, and so it's kind of going a little out of control. But right, you saw the box expanding. So let's add some more. And obviously now I exploded my box. But right, that kind of, again, makes sense, right? Add more things, and then increase volume to, again, keep our pressure constant. And so we have this relationship here. And so then, again, we get our equation. So our V1 now over N1 is equal to V2 over N2. Again, the units for volume don't matter as long as they're the same. And then N has to be in moles, so we don't really have another way of expressing that. So just keeping with our moles relationship. And so again, right, our volume of gas is directly proportional to our number of gas molecules. And obviously, right, if we physically have more gas molecules, then you're having more collisions. So to keep our pressure constant, then our volume must increase. So let's see if we can do our little sample problem here. And so now we're saying, okay, we have this male athlete, and their initial lung volume is 6.15 liters, so during a super deep inhalation. And so let's just say at this volume, his lungs contain 0.254 moles of air. And then during exhalation, lung volume decreases to 2.55. And so this is a little tricky how it's worded, because then it asks how many moles of gas does he exhale during exhalation? So I rewrote our relevant formula and then see if you can solve this. so let's see how your setup went. So we have our initial conditions, right? 6.15 liters, and we said initially contained 0.254 moles. And so then we decrease volume to 2.55 liters. So now we can solve for x. But what are we solving for when we solve for x? So what is that?
The difference of air from the start to moles of air at the end.
Yeah, so this is right, so it's still moles right in the lung. So let's do that. So 2.55, oops, times 0.254, and divided by 6.15. So then we have 0.015 moles, right, remaining in the lung. So moles still in our lung. So did everybody get this number? All right, excellent. But then, right, the question, though, actually asks how much did he exhale? So then to figure out our exhale, you just had to do the subtraction, so 0.254 moles minus 0.105. And so then we get, right, that about 0.149 moles exhaled. Any questions on this one? And so now we go to our ideal gas law. And so kind of my problem, not really my problem, but I feel like, right, it can feel like too much memorization. You got all these formulas, blah, blah, blah. And so really, though, all we need to know is PV equals nRT. And so we can figure out what to do with this. And so there's a couple of different things. So first of all, this is our ideal gas law. And so this is our relationship that connects all of them, right? So now this relates pressure, volume, moles, and then we'll go through. So R is a constant, and then of course temperature is in Kelvin. So our R is 0.0821, and so that's down here. So this is just defined as our ideal gas law constant. And so let's talk about the units, though. And so if we go to, well, let's just watch. So we're on our search engine, ideal gas constant, and then it gives you something different. Or rather, if we even go to this Wikipedia page, it gives us a ton of other gas constants. And so before we get totally overwhelmed, right, these are all just depending on your units. So it's always a gas constant. It just depends on what your other units are. And so let's scroll down and find the one we just learned. And so, right, we're working with liters. So, right, we're in liters for volume, ATM for pressure, and we'll get into that, this Kelvin, and then, of course, moles. So this is, right, the gas constant we were just presented, 0.082. We just round it to 1, but, you know, you can see it goes on and on. And so when we use this gas constant and we use this formula, so now the units matter. So units matter. So again, it's dependent on this gas constant. So now pressure has to be in ATM, right? Our volume has to be in liters. And then, of course, N is always moles. And then temperature is always Kelvin. All right, so does that kind of make sense? So for the comparative ones, right, the units didn't matter so much. But for this one, it's, again, all dependent on this gas constant and those units. And so this just reiterates it. And so now they kind of show us that we can take this and derive our different gas laws. And so this is where I like the formula. And let's actually show kind of other relationships. And so let's do a tiny, tiny derivation. And so we're given, right, our ideal gas law formula. So PV equals nRT, but R is a constant. So we can rewrite our formula as PV over NT equals R. So then we can set up any initial conditions. So we have P1 V1 over N1 T1 is equal to R. But that also means that we can have, right, a second set of conditions equal to R. So P2 V2 over N2 T2. And since they're both equal to R, we can now just set them equal to each other. And so now we're left with P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so I like this form a lot. So this is kind of another combined ideal gas law formula. But what do you start to notice about this? What does it kind of look like? So notice you start to see your other formulas in there, right? Because then we have P1 V1 equals P2 V2, but that's holding, right, our moles and temperature constant. So if we hold those constant, that just gives us this back out. So same thing, right, with our other gas laws. So we said we had V1 N1 equals V2 N2, right, for Avogadro's number, or Avogadro's law. So again, holding pressure constant and temperature constant, so you get out that relationship. And then we can get out our other one, so our V1 T1 is equal to V2 T2. So again, holding the other variables constant. So is that kind of making sense so far? So we want to see, right, that we're just re-deriving these relationships. Because again, right, we don't necessarily want to stress out, be trying to memorize all these formulas. What we care more about is just, again, right, getting our relationship. And then we haven't seen a problem like this, but this is also a way to handle a change, right, in either 3 or 4 variables. And so all I mean by that is we could, of course, take the most extreme, where we change, right, our pressure, volume, moles, and temperature to get new pressure, volume, moles, and temperature. Or sometimes maybe we'll hold the temperature constant, so then you can get your new formula. So basically any variable that's held constant goes away. Right, so constant variable cancels out. So i.e., right, hold temperature constant, and then we get out our new formula. So if we hold temperature constant, that eliminates temperature. So then you get P1 V1 over N1 is equal to P2 V2 over N2. So this, again, our kind of combined gas law is a good way to rederive any other formula or relationship we need. So other than, right, just the 3 basic gas laws that we were presented. And I'll try to bring a practice with this, if not today, then Wednesday. And let's see what else is useful. Oh, other things that we should kind of mention. So again, we have our PV equals nRT if we're not given, you know, initial and final conditions. So this is always a good formula. But then let's look at a couple of other things, because we mentioned some relationships back here. So let's go back. So, right, we had said, for example, that pressure and volume had an inverse relationship. And so now we can see that better on this formula. So they're on the same side. So anything that's on the same side has an inverse relationship. So then we could say, you know, like moles and temperature, so those would have an inverse relationship as well. So moles and temperature, right, they're on the same side. So if one increases, then the other has to decrease. And then kind of the other thing, so if they're on opposite sides though, so we had looked at, if we go back to our laws, so we had said, okay, Charles's law, volume and temperature have a direct relationship. And so if we look right now, they're on opposite sides. So now they have a direct relationship. So now if one increases, right, the other has to increase as well. And so same thing, right, like pressure and moles, so those are directly related. So anything that's on opposite sides, we can say something about the relationships, right? So those are opposite. So, sorry, opposite sides, so pressure and moles. So equals direct relationship. So again, if one increases, so if pressure increases, that means our moles must be increasing as well. Does that kind of make sense? So you can kind of do an analysis of any two variables. So anything, again, opposite sides, direct relationship, same sides, inverse. And then again, right, this is just re-emphasizing kind of our derivation. I prefer kind of this form just because to me this is easier to see. Again, things hold constant, cancel out, but you can still see, again, how we got that relationship. All right, so let's try this one. So now I think we're going to need our new formula. So PV equals nRT. And don't forget our R, 0.0821. So that's for moles, liters, ATM, Kelvin, to just kind of remind us of our units. So I'll keep saying that, right? Gas constant units defines these units. how's our work coming along? Did we get an answer? So it looks like this was fairly straightforward for y'all. So, right, we just have our PV equals nRT. And then it just so happened, right, that everything is already in the units that we need. And so it's asking for volume. And so that's really the hardest part of the problem, is just kind of plugging everything in. And so again, we're in ATM, so that looks good. We don't need to do any conversions, so we're trying to find volume, so that'll be X equals, so then we have 0.845 moles times our gas constant, and then temperature, right, was already in Kelvin, so pretty nice situation here. And 0.845 times 0.0821 times 315, and then divided by 1.37. So did we get 15.95 liters for the volume? So I see lots of nods. Excellent. And should round it to 3 sig figs, so 15 point, oh, that rounds us to 16.0 liters or so. All right, sounds good. And so let's continue on. And so this is really helpful as well. So now let's go into our standard conditions. And so we have what's called our STP. And so this is just something that, again, you see in like problems, and people kind of define this. And so let's kind of see the relevance. And so we have our standard pressure. So that's just defined as 1 ATM. Standard temperature is 0 Celsius or 273 Kelvin. And then 1 mole. And then this is the really important part, is that you have this standard volume is 22.4 liters. And so what this means, and this is, again, the next kind of important logical step, is that 1 mole of gas at STP is our molar volume. And so it doesn't matter, again, what the identity of the gas is, 1 mole is always 22.4 liters. And so in actuality, there is a little bit of variation, since again, right, gases don't behave ideally, but it's still pretty close to 22.4 liters. And so then let's look at some of the problems, because then you start to get, you know, kind of problems that sound hard but are easy if we use this relationship. So now we can say, so at STP, we have .5 moles of gas. So what is the volume? So let's start with something easy. So how would you solve that? So what's our volume? 0.5 moles. We have our STP relationship. What do we get? I think we're thinking too hard. So right, set up a proportion. So we have our STP, so we can set up, well, I know 1 mole at STP, right, is 22.4 liters. So then we can easily set up our proportion now. Well, if I have 0.5 moles, what's our volume? So now what's our volume? This is easier to see. So now we can see, right, it's 11.2 liters. And so now let's try another tricky one. So at STP, I have 4.2 times 10 to the 24th molecules of a gas. What is the volume? So how can you make this problem easy? Think of your proportions. Think of what the STP means, right? Think of this. Think of our volume. So what do we get? Any ideas on how to set this up?
Would it be 1 molecule over 22.4 liters?
So not 1 molecule, but go back. So how many molecules do we have, though, at STP? How many? Yeah, so right, so we have to remember our definition of STP. So yeah, we're saying we have 1 mole, and so that's 6.022 times 10 to the 23rd molecules. And it doesn't matter who you put on top or on bottom, just as, you know, it's consistent. So I just picked molecules on top. And so it's asking for volume, so I'm just going to go to the direct relationship so that, again, at STP, we have 1 mole or 6.022 times 10 to the 23rd molecules at 22.4 liters. And so now this makes this nasty looking problem a lot simpler, right? So now we can just set up our proportion. So we have our molecules and then volume. And so now we can just do our cross multiplication. So 4.2 times 10 to the 24th times our 22.4 liters, and then divide it by Avogadro's number. And so now we get that this is 156 liters. And so that makes sense, right? We have many more moles. We could even, right, kind of divide it. Let's do a sanity check for ourselves. So divide it by our number of moles. And so that gives us, right, 7 moles approximately. So that makes sense, right? 7 times 22. So that gives us back to our 156. So just kind of helping you. And then you don't have to go through, right, the 2-step conversion of figuring out moles and then going from moles to liters. So we could have done that. So we get the same answer, right? But just using the proportions is a little bit simpler. Does that kind of make sense with how to use the STP to help you? So hopefully it helps you kind of simplify problems and again see those relationships a little easier. Otherwise, you know, you can always go back to PV equals nRT. So if we're talking, you know, about kind of safe spaces in chemistry, I think this is a good kind of safe space to be. And so, right, I would have that formula really prominent because you can, you know, again, derive all your relationships from there. All right, let's see. I think we have enough time for Dalton's law. And so Dalton's law is now just stating that our total pressure of a gas mixture is the sum of the partial pressures. And so let's again think about what this is saying. And for our assumptions, again, our particles have negligible sizes. We're assuming no intermolecular forces. And so we're saying that particles of different masses have the same average kinetic energy. And so our average kinetic energy is the same, so our total pressure of our collisions is the same. And so now let's think about this in terms of kind of our air that we breathe. And so first of all, right, again, it's just saying you sum up all the pressures. So our P total is our pressure of component A plus compression of component B and compressor of component C. And again, gases behave independently, so we can just kind of analyze one gas at a time, again, as long as we add up our pressures. And so this is just going through the derivation, again, how we get this relationship. And then it brings us to kind of mole fraction, which is similar, but again, we're kind of dancing to our example. And so we say, well, our component, our percent component of whatever part, now let's talk real. So let's just say we're talking about air, right? And so nitrogen, do people know how much nitrogen is in the air? 70-something%. Yeah, so right, our air is about 78% nitrogen. And so now we can say, all right, so here's our pressure total. And so this is also implying, again, if pressure is additive, that assuming we're at 1 atm, then we have 0.78 atm of nitrogen. So that's all this relationship is saying with our mole fraction. And so this would also be proportional to our total number of moles, so we could figure out, right, total gas moles and then moles of nitrogen, and again, it should be 78%. And then, so this goes back to our mole fraction, so kind of what we were saying with nitrogen. So we should get that it has a mole fraction of 0.78, which then, if we multiply it by our total pressure, so right, this is our total pressure, assuming we're at 1 atm, then again, we get back out our pressure of nitrogen is 0.78 atm. And then thinking about, right, our total major components in our air, so of course, right, nitrogen is a majority at 78%, and then oxygen is about 21%, so that's reflected by the 0.21 atm. And then argon is already, right, at 1% of the composition, or about 0.01 atm. And then, of course, right, other negligible gases, CO2, argon, or we already said argon, krypton, CO, etc. Questions about this kind of partial pressure additive? All right. we should probably at least start our phase changes. And so now we want to get into kind of phase changes. So this is related to our gas laws, but now kind of taking it to the next step, right? So kind of the distinction between what we were talking about and where we were going is we were saying, well, identity doesn't matter, right? Our gases all behave the same, blah, blah, blah. Well, we know that's actually not true, right? Different substances obviously behave differently, but now we want to get into the why. And so again, right, we have our general recap. Well, we can, of course, do our state changes by adding heat. And so if we go, right, our solid to liquid, so this is endothermic. So now thinking back to our energy chapter that we just kind of rushed through. Though everything feels rushed in our 10-week terms. So right, endothermic, meaning we have to add heat. So then that's increasing energy. And then again, add heat again, endothermic. And then we go from liquid to gas. And then, of course, right, these processes are exothermic, the reverse of cooling. And so now we want to get into, again, right, the why. Well, why are things, again, why are some things a liquid? Why are some things more volatile? Why are some things a solid? And so now we actually want to get into the differences and start looking at those intermolecular forces. And so now is at least a good time to do our word analysis. So inter, and this is between molecules. And so this is a really important distinction. I've seen, OChem students still kind of mess this up. So our intermolecular forces are just these forces that are between molecules, right, that kind of hold them in their form. So, right, if they're a solid, then they have pretty high intermolecular forces that keep them in their solid state. Liquids, again, they still usually have pretty strong intermolecular forces. And so the way to remember this is, right, we have our interstate highway. So that's going to be between states. And so contrast that with our intramolecular forces, our intra-state highways. So intramolecular forces are going to be right within our molecule. And so our intramolecular forces, those are the ionic bond or the covalent bond, right? So what's actually holding your molecule together? And these are a lot higher in energy, right? They're a lot stronger compared to the intermolecular forces that just kind of keep them bound. And so again, we're talking about, so then we would have our intramolecular forces, right, covalent bonds. And then we'll get into the intermolecular forces. And so looking at our water molecule, actually let me redraw it. And so we'll learn about hydrogen bonding coming up. And so that's going to be our forces between other molecules. So now our intermolecular forces are going to be kind of this interaction. So force between molecules. And so later we're going to learn in a few minutes or tomorrow or Wednesday that this is hydrogen bonding. And so we're starting to get a peek, right, at, again, those intermolecular forces. And so we're starting to answer why water is a liquid at our ambient temperature. So it has this hydrogen bonding, again, our intermolecular forces that keep it as our water, right, as opposed to just kind of flowing off and being in the gaseous state. Because actually water, you would expect it to be a gas just purely based on its molecular weight. And so we'll get into that. And So a few more minutes of class, so we at least want to define what we'll be looking at. And so this is just a quick recap. So all attractive forces are electrostatic in nature. So again, think of the ionic bond, right? That was just a positive charge and a negative charge. So opposites are attracting. And so that's the same sort of thing, right? We're still kind of thinking of these positive, negative charges coming together, or like polar, nonpolar, or two polar things. So we'll be examining that. And so this is really where the interesting part comes into play, or at least what I find fascinating, right? So the strength of those interactions then determines its state. So again, that's where we're going to be trying to understand more, why is water a liquid? Why is it not a gas? And so at room temperature, if we have moderate to strong attractive forces, then right, we see our material as being a solid or a liquid. And so our stronger the attractive forces, the higher the boiling point. And that makes sense, right? So if they're really stuck together, then you have to add more energy to, again, break apart the intermolecular forces. So again, we're not breaking bonds, right? So we're not trying to break our covalent bond. We're just trying to break these attractive forces, again, going from, let's just say, our liquid to gas state in our transition here. And so, again, we'll probably have to save this for Wednesday, but we'll start to look at those attractive forces because they vary in strength, and so we'll look at that, and we'll look at how it depends on the types of particles, and we'll get into kind of nonpolar versus polar again. So kind of being able to identify our polar molecules will become relevant. All right, I think we'll stop there so you can kind of see where we're going. And so we'll pick back up on these electrostatic interactions and then start looking at our intermolecular forces on Wednesday. So we'll keep up with that. All right, have a good Monday. See you Wednesday. If anyone needs help, just let me know.